diving deep into quantum source.
Quantum source.
Yeah. They're trying to build quantum computers, but like not the huge ones.
Oh, okay.
They want to make them like fit in a normal room.
Wow, that's ambitious. Instead of these giant factory-sized things.
Right. And what's interesting is how they're going about it. So you know how there are like two main approaches to quantum computing?
You mean like photonic and atomic?
Exactly.
Yeah.
Quantum source is kind of saying, why not both?
Interesting. It's like they're merging those two paths. That's a pretty bold move.
Yeah, instead of picking a side, they're combining them, which could be huge. I mean, think about it.
Yeah.
If they can pull this off, it could totally change the game for how affordable and scalable these things are.
Right, because if we want quantum computers to actually be useful, they can't just be these giant, expensive machines that only like governments and huge companies can afford.
Exactly. So how does it even work? This whole merging thing, I mean,
Well, the core idea is that they're using photons for the actual computing part.
photons, like light particles,
Yep, that's the photonic side of things. But then for entanglement...
which is, just to remind everyone,
Oh, right, sorry.
like the secret sauce of quantum computers.
Yeah, it's what links the qubits together.
Right, gives them that extra power.
Exactly. So for entanglement, they're using atomic qubits.
Okay.
Specifically made of rubidium atoms.
Rubidium atoms. Why rubidium?
That's a great question. So rubidium atoms, they're really special because every single one is exactly the same.
Really?
Yeah, like no matter where you find them in the universe, they're identical.
Huh. That's kind of mind-blowing.
It is. And for building a reliable quantum computer, that's super important. You want consistency, right?
Yeah, like if you're building something, you want all the bricks to be the same.
Exactly. Imagine trying to build a house where every brick is a slightly different shape and size.
Yeah, that would be a disaster.
Total mess. So yeah, using rubidium, it's like quantum source is making sure every photon is a perfect replica of the others.
Okay, I'm following. So that minimizes errors from the get-go.
Right.
But aren't atoms like super sensitive? Doesn't everything mess them up?
Well, yeah, usually. But that's another cool thing about rubidium. They're actually really good at ignoring that environmental noise.
Oh, wow.
Yeah, which is key for keeping the qubits stable. It's like
Wow.
they've got these perfect little quantum building blocks
Right.
that aren't affected by the weather or anything.
That's incredible. So you've got these perfect, stable rubidium atoms
Yeah,
pumping out these perfect photons.
right.
But how do they actually interact? Like, do photons usually just, like, zoom past each other?
You're totally right. Photons are kind of like those lone wolf particles. They don't usually interact with each other much.
Right.
And that's a huge problem in photonic quantum computing.
Yeah, I can imagine. You need those qubits to, like, talk to each other.
Exactly. They need to interact in very specific ways to do these calculations.
So quantum source is using the rubidium atoms as these intermediaries
Oh, I see.
to help create those interactions in a controlled way,
So instead of just hoping that the photons bump into each other.
which would be, like, incredibly inefficient.
Yeah,
They're using the rubidium to make sure it happens reliably on demand.
that's pretty smart. But isn't working with individual atoms, like, crazy difficult and expensive?
Well, it definitely can be, especially with how photonic quantum computing is usually done.
How do you mean?
A lot of the traditional methods, they rely on probabilistic processes.
Probabilistic.
Yeah, meaning it's kind of like you have to try a bunch of times and hope you get lucky.
Oh, like you have to run the experiment over and over?
Exactly. It's almost like trying to win the lottery.
Wow. And I'm guessing that eats up a ton of resources.
Oh, yeah, it can be a huge resource hog, like trying to build a giant factory just to get a few usable photons.
So not exactly efficient if we want these quantum computers to, actually be out in the world.
Right? It defeats the whole purpose. So how does quantum source change that?
Their approach is what we call deterministic.
Deterministic.
Yeah, so basically each rubidium atom, it spits out a photon with very specific properties.
Okay.
And they can control that really precisely.
So no more hoping for the best.
Exactly. No more relying on chance.
That's got to make a huge difference.
It does. It means way fewer resources get wasted, so it's way more efficient.
So it's like going from that giant, messy factory
Yeah.
to this really sleek, efficient machine.
Exactly.
Now, that's what I'm talking about. Efficiency is key. And it's not just about speed, right?
No, not at all.
It's about tackling problems that regular computers just can't even touch.
Absolutely. Like problems that would take a normal computer like millions of years.
Okay, so we've talked about how they make these photons.
Right.
But how do they actually use them for, like, real calculations? What about all the stuff we hear about, like error correction and those,
Logical qubits.
yes, logical qubits, those bigger, more stable ones?
Yeah, those are great questions. And honestly, those are some of the biggest challenges in the whole field of quantum computing.
I bet. I mean, we always hear about how fragile these qubits are,
Oh, yeah, they're super prone to errors.
and then trying to build a computer with millions of them.
Right. Scaling up like that is incredibly difficult.
So how does quantum sources approach help with that?
Well, because they're generating such high-quality photons from the start with really low error rates, it makes the whole error correction process a lot easier.
Oh, that makes sense.
It's like if you're building a house and you start with really strong, well-made bricks,
Right.
the whole structure is going to be more stable.
Okay, that's a good analogy. But why rubidium? I'm curious, are there other things they could use for those, what did you call them?
Quantum emitters.
Yeah, quantum emitters.
There are other options, yeah.
Like what?
Like some materials have things called nitrogen vacancy centers
Okay.
or quantum dots,
Huh.
but those often come with their own problems, you know?
Yeah.
They can be more sensitive to noise. Oh, right.
And they can be more variable, which means more errors can sneak in.
I see.
It's kind of like the difference between a perfectly tuned musical instrument
Yeah.
and one that's a little bit out of tune.
Right, it's not going to sound as good.
Exactly.
Yeah.
So rubidium, even though it's tricky to work with, it gives you that really precise control.
It's like that perfectly tuned instrument.
Yeah, giving you those really pure photons.
Cool. But wouldn't trapping and cooling those atoms require, like, a ton of equipment?
You'd think so, right?
Yeah. Like, how does that fit with their whole thing of making these smaller computers?
Well, they've actually developed some really clever techniques
Oh.
to trap and cool the atoms with really high stability and precision. And get this, the whole system, except for the detectors, it operates at room temperature.
Whoa, really?
Yeah.
That's huge.
Yeah, it is. It makes the technology a lot more practical.
Okay, so they've got these super stable, high-quality qubits, and they don't need to freeze the whole computer.
Right. That's awesome.
Yeah.
But how do they scale it up? Like, to actually have millions of qubits?
Right, that's the big question, isn't it?
Yeah. Wouldn't that take, like, exponentially more resources?
Well, that's where the beauty of their deterministic approach really comes in.
Okay.
So remember how we talked about those probabilistic systems needing more and more resources as you scale up?
Yeah, like it gets out of control.
Exactly. It's exponential growth.
Mm-hmm.
But with quantum sources system, the resources only grow linearly.
Linearly?
Yeah. So they can just add more and more devices as needed.
Oh, it's way more manageable.
Right. It makes it a lot more sustainable.
So instead of building a giant factory,
Yeah,
they're creating this modular system.
exactly. Like connecting Lego bricks.
I like that analogy.
Yeah.
But I'm guessing there are still challenges, right?
Oh, absolutely. There are always challenges when you're pushing the boundaries of technology like this.
Like what? What are some of the things they're still working on?
One of the big ones is optimizing those tiny resonators they use.
is.
Yeah, think of them like little antennas
Okay.
that help control the atoms and like measure what they're doing.
So they're super important.
Oh yeah, they're critical. And getting them to work perfectly, especially as they add more and more of them, it's a real challenge.
Yeah, I can add
It's
it.
like a really delicate balancing act.
So it's not just about trapping the atoms.
Mhm.
It's about making sure their whole environment is set up just right.
Exactly. You need those atoms interacting with the photons in a very specific way.
It sounds incredibly complex.
It is. And then there's also the coupling efficiency.
Coupling.
Yeah, it's basically how well the photons and the atoms can, like, talk to each other.
Okay.
The better the connection, the better the quantum computer will perform.
Makes sense. So stronger connection, better performance.
Right. And then you've got the challenge of building these switching mechanisms.
Switching.
Yeah, to control how the information flows between the qubits.
Oh, so it's like they're building this quantum superhighway,
Kind of, yeah.
making sure the traffic moves smoothly and the signals are clear.
Exactly. And all of this while still keeping those rubidium qubits super stable and high quality.
That's their motto, right? Quality, quality, quality.
Yeah, that's quantum source for you.
It really makes sense now. But I want to zoom out for a second.
Oh.
We've been talking about all these technical details.
Yeah.
But what's the big picture? Like, what could we actually do with these room-sized quantum computers?
Oh, the possibilities are like mind-blowing. Imagine being able to design completely new materials with properties we haven't even thought of yet.
Like what? Give me an example.
Okay, like super efficient solar cells or maybe ultra strong, lightweight materials for building spacecraft.
Whoa. Space crash.
Yeah, or think about drug discovery. We could use quantum computers to simulate how molecules interact with incredible precision.
And that would help us do what?
Develop new drugs. Drugs that are more effective and have fewer side effects.
Where? That would be huge.
It would. We could revolutionize entire industries, from medicine and materials science to energy and aerospace.
It's almost overwhelming to think about all the potential.
It is.
But I want to go back to something you mentioned earlier. You said quantum sources approach is deterministic.
Right.
And a lot of other photonic systems are probabilistic.
Yeah.
Can you, unpack that a bit more?
Sure. So in those probabilistic systems, the resources you need, they grow exponentially as you add more qubits.
Exponentially.
Yeah. It's like, imagine you're building a tower out of cards.
Oh, okay.
The bigger you make it, the more unstable it gets.
Yeah, it's going to fall apart.
Right. But with quantum sources' deterministic approach, the resources only grow linearly.
Linearly meaning?
It's much more manageable. Like, if you're building a house with a strong foundation, you can add more floors without worrying about the whole thing collapsing.
So deterministic means predictable and scalable.
Yeah.
And probabilistic means, more uncertainty and a much steeper resource curve.
Exactly.
It's clear why they're going with deterministic. But I've heard some people are skeptical about whether atomic systems can really be scaled up enough.
Yeah, I've heard that too.
Even with rubidium, it still seems like a huge challenge.
It's definitely a valid concern, and it's true, there are still a lot of technical challenges.
Right.
But we have to remember, this technology is still pretty young.
Yeah, that's true.
And we've seen some really impressive progress. And the pace of innovation is just getting faster.
That's exciting.
It is. And I think quantum sources focus on quality combined with their, modular approach to scaling.
Right, like Lego bricks.
Exactly. It gives me a lot of confidence that they're on the right track.
It sounds like they're being really careful and methodical.
They are. They're not rushing into anything.
Which is probably a good thing.
Yeah, better to build a solid foundation.
Okay, but even if they can build these room-sized computers, what about access?
Access.
Yeah, will this technology only be available to big institutions and governments?
That's a great question, and it's something that Quantum Source seems really aware of.
Okay.
Their whole thing about making the system work at room temperature.
Right, except for the detectors.
Yeah, that's a big step towards making it more affordable and practical.
I see. So it's like, instead of needing this giant specialized freezer, you just need a regular refrigerator.
Exactly. It could be a game changer for accessibility.
That would be amazing.
Yeah.
But quantum mechanics is, notoriously complex.
It is.
So even if the hardware is more accessible, wouldn't you still need to be, a physics genius to use it?
Well, that's where software comes in.
Software.
Yeah. Think about it.
Yeah.
In the early days of computers, you had to be a programmer to use one.
Right.
But now, thanks to all the user-friendly software, anyone can use a computer.
For pretty much anything.
Exactly. And the same thing is happening with quantum computing.
Really?
Yeah. There are all these new tools and platforms being developed that hide all that complex quantum mechanics stuff.
So you don't need a PhD to use it.
Exactly. It's all about making it accessible to people from all sorts of backgrounds.
So we're not talking about replacing everyone with physicists.
No, not at all. It's about giving people new tools and skills.
That's great. But what about education? Are we preparing people for this quantum revolution?
Yeah, that's definitely something people are thinking about. More and more universities are offering courses and degrees in quantum information science.
Wow, so it's becoming a real field of study.
It is. And even in high schools, they're starting to teach kids about the basics of quantum computing.
That's awesome. Get them interested early.
Exactly. The goal is to build a whole pipeline of talent.
But it's not just about formal education, right?
Oh, definitely not. There are tons of online resources available.
Like what?
Like videos, articles, tutorials, even open source software platforms.
Wow. So there are ways for anyone to learn about this stuff.
Absolutely. There are even online communities where people can connect and share ideals.
That's really cool. So it's not just about technical skills, right?
No, not at all. It's also about like creativity and critical thinking.
Yeah. Collaboration.
All those skills that are going to be super important in this new quantum world.
Exactly. Quantum computing, it's not just about the technology itself. It's about the people.
Right. The people who are building it, using it, and figuring out how it's going to impact society.
Exactly. We need all sorts of perspectives to make sure it's used ethically and for the benefit of everyone.
That's a great point. Well, this has been an amazing deep dive into quantum source and the whole world of quantum computing.
It has.
We've covered so much.
We have.
From the nitty-gritty details of their technology
Yeah.
to the potential applications and all the ethical stuff we need to be thinking about.
It's a lot to take in.
It is. So is there anything else you think our listeners should know as they, process all of this?
I think the most important thing to remember is that quantum computing, it's not just some sci-fi fantasy anymore. It's a real thing, and it's developing really fast.
Right.
So it's important to stay informed and engaged. Couldn't agree more. Well, a huge thank you to our expert for guiding us through all of this.
Oh, it was my pleasure. I always love talking about this stuff.
I can tell. And to our listener, we hope this deep dive has, sparked your curiosity.
Yeah, get out there and explore.
Exactly. The future is being shaped right now, and we can all be a part of it.
That's the exciting part.
It is. Thanks for joining us, and until next time, keep diving deep.
It's kind of like, we've got the hardware becoming more accessible,
Right.
but now we need the software to catch up.
Yeah, to make it user-friendly for everyone.
Exactly.
So are people working on that?
Oh, yeah, definitely. There's a ton of research going on in that area.
What kinds of things are they developing?
Well, they're building all sorts of tools and platforms that, hide all the complexity of the quantum mechanics.
So they need to be a quantum physicist to use them.
Exactly.
That's great. So it really could be accessible to people from all sorts of backgrounds.
Yeah, like biologists, chemists, financial analysts.
Anyone who needs that extra computing power.
Right, and they wouldn't need to become experts in quantum physics.
They could just focus on their own field and use these tools to help them.
Exactly. That's the goal, anyway.
I like that. But what about training and education? Are we preparing people for this, quantum future?
Definitely. There's a growing awareness that we need to start teaching people about this stuff.
Yeah, it seems like it's going to be pretty important.
It is. So more and more universities are offering courses and even whole degree programs in quantum information science.
Wow, so it's becoming a real field of study.
Yeah, it's really taking off. And even in high schools, they're starting to introduce some basic concepts.
That's cool. Get them interested early.
Right. It's all about building that pipeline of talent.
Yeah, it makes sense. This technology is only going to become more important.
Absolutely.
But it's not just about formal education, is it?
No, not at all. There's so many other ways for people to learn about quantum computing.
Like what?
Well, there are tons of online resources. You can find videos, articles, interactive tutorials.
Cool. So if you're curious, you could just go online and start learning.
Exactly. And there are even open source software platforms where you can get hands-on experience.
Wow. So there are really opportunities for anyone to get involved.
Yeah. If you're interested, there's a whole world out there waiting for you.
That's amazing. So it's not just about learning the technical stuff either.
Right.
It's about fostering creativity and critical thinking.
Yeah. And those collaborative skills.
Right, because you're going to need to be able to work with others.
Especially in a field as complex as this one.
It's like quantum computing is bringing together so many different disciplines.
It is. It's really interdisciplinary.
And that's what makes it so exciting.
Absolutely.
Well, this has been an incredible journey into the world of quantum source and the whole quantum computing landscape.
It has been.
We've talked about so much, from the technical details to the potential applications and the ethical stuff.
And everything in between.
Yeah, it's been a wild ride. So as we wrap up here, is there anything else you want to leave our listener with?
I think the main takeaway is that quantum computing is here.
It's not just a sci-fi dream anymore.
Exactly. It's real, and it's happening now.
So we need to pay attention.
We do. And stay curious.
Couldn't agree more. Well, a huge thank you to our expert for guiding us through this.
Oh, it was my pleasure. Seriously, I love talking about this stuff.
And to our listener, we hope this deep dive has inspired you to learn more.
Explore. Ask questions.
Exactly. The future of quantum computing is being written right now, and we can all be a part of it.
That's what makes it so exciting.
It really is. Thanks for joining us, everyone, and until next time, keep diving deep.